you want to produce small numbers of fairly large components, then using sand molds to cast them is an ideal way to do it. It is at the moment the best method for metals which melt at high temperatures. But there are disadvantages. A new mold has to be made for each casting, and if you want to make 500 or more, the technique is quite uneconomic, particularly for low melting metals. There's often a need to turn out a huge number of small, light castings with great accuracy and so good a surface that only a little finishing needs to be done to make them perfect. Here, die casting is the answer. Metals with a relatively low melting point are used in die casting, and the molds are used over and over again. The aim is to produce castings with a high degree of accuracy, a good surface finish, and to get as many components from one set of dies as possible. Die casting is an excellent technique for making things like transmission cases, carburetor parts, and certain types of car wheels. The simplest way of die casting is to pour the metal from a ladle and let it fill the die under gravity. Here they're using gravity die casting to produce high-performance wheels for racing bikes from magnesium. The mold, we call it the die, is made from a fine-grained cast iron, and it consists of two halves. First, a sand core is fitted to the center of the bottom half, and the whole area is blown clean with compressed air. The two halves of the die are then dusted with a fine white refractory powder. In this case is a mixture of French chalk and boracic powder. This helps to prevent the metal chilling prematurely and stops it sticking to the dies, lessening any erosive action which the molten magnesium might produce on the surface of the die. The three sides of the bottom die are locked into position and the two halves are joined. They're locked firmly together, and the whole die is tipped at an angle ready to receive the molten metal. At this particular foundry, they're heating the magnesium to 790 degrees centigrade in these gas-fired furnaces. Magnesium melts willingly at this temperature, but if mixed with oxygen from the air in these conditions, it can also burn explosively. To prevent this happening, the metal is kept under a flux in the furnace so that it won't come into contact with oxygen in the air. Around the die is a ring of gas burners, which not only help the molten magnesium to flow smoothly into the die, but also maintain the correct thermal gradients during the cooling period, ensuring the metal doesn't solidify before it fills the cavity. While the metal's being poured, sulfur powder is dusted over the parts of the die where it'll flow. As the metal runs, the heat causes the sulfur to combine with the oxygen in the air, creating sulfur dioxide gas. This is much heavier than air and provides an inert gas blanket for the molten magnesium. This keeps the metal surface clean and shiny and prevents it from catching fire. Once the metal is seen to appear in the risers, the pouring ends, and the casting is left for 7 or 8 minutes to cool. The top half of the die, the core, can then be removed. Immediately it's dusted with the boracic powder and French chalk, ready for the next casting. The bottom half, which holds the casting and its runners and risers, breaks into 3 pieces so that the casting can be released easily. It's now fallen to a temperature of 400 degrees centigrade, and it can be handled, carefully of course, with a pair of tongs. Each wheel is stamped with the date and the batch code number so that it can be traced back to its origin if there should be any fault or failure in the future. After further cooling, the wheel is checked for any major defects. A dye known as engineering blue is painted onto the wheel. As the spirit in the fluid evaporates, it leaves the blue colorant behind to reveal any telltale cracks. The finer cracks, should there be any, are detected by irradiating the wheel with ultraviolet light at a later stage. If there are no cracks, then the runners and risers are removed by cutting them off with a large bandsaw. The waste material left behind can be processed and used again. Finally, the wheel goes for heat treatment. The whole process resembles some ancient tribal ritual, but it works. Molten magnesium is a difficult metal at the best of times, but if you want light, strong components like these racing wheels, then magnesium is the best metal and gravity die casting the best production technique. A much easier metal to die cast is aluminium, and it's become increasingly popular in the production of road wheels for the more expensive cars with a sporting image. Because aluminium melts readily, it's an easier metal to work with, and it lends itself to automation. In this foundry, they're using a technique known as low-pressure die casting. A low pressure is applied to the surface of the metal to force it into the die. The aluminium ingots are melted in a series of gas-fired furnaces. Then the metal is poured into a smaller mobile ladle and checked to see that it is at the correct temperature. The ladle can be used to fill any one of the die casting machines. Because aluminium doesn't burn readily in air, and because it flows easily, rather like water, it's a much easier metal to handle than magnesium. Up to 500 pounds of molten aluminium can be kept in a heated furnace under each die. Each charge of metal is sufficient to form 12 car wheels. A real bonus of this automated system is that you can top up the reservoir of metal while a casting is cooling in the die. At the start of each cycle, the sides of the bottom half of the die come together, and the top half descends to form a tight seal. The die is surrounded by a series of gas burners, as we saw in the gravity die casting process. This helps the metal to flow freely into the die and maintains the correct thermal gradients during cooling. A low air pressure, about 6 pounds per square inch, is then applied to the molten aluminium in the reservoir underneath the die. This increase in pressure forces the metal up the venturi tube and into the cavity of the die until it's completely filled. Solidification begins at the edges of the rim and works progressively inwards. When the casting has completely solidified, the die is opened and the casting removed. One of the great advantages of the process is that there's very little waste, as there are no runners and risers to remove. Finished wheels are marked so that they can be identified at the checking stage. When the wheels have cooled, they're checked for major defects, and if they're accepted, they're dated and batch stamped. With no runners and risers to remove, the wheels need only a small amount of fettling and a minimal final machining. Low-pressure die casting is an ideal method for this kind of component. Each of these machines can produce up to 85 wheels a day, and the whole production unit can turn out around 4,000 castings a week. If you could shorten the time the metal takes to cool in the die, you could significantly increase your output, and this can be done. One method is to inject the metal under a high pressure into a water-cooled die. The technique is known as high-pressure die casting. The metal is injected into the die with a plunger, which can exert a pressure of up to 14,000 pounds per square inch. The die itself is mounted between the two plates of a horizontal press. The press has to lock tight so that it can stand up to the high pressures exerted, and it'll vary according to the size of the casting. Between each injection of the metal, the die is sprayed with a graphite-based oil to help prevent the metal sticking to it. Because of the high pressures involved, safety regulations mean that the machine is heavily guarded. The metal injection plunger on the machine moves in 4 phases. The closing of the pouring hole, moving the metal up to the gate in the die, a very rapid movement to fill the cavity as quickly as possible, and last, an intensification to compact the metal and reduce cavitation. That way you should end up with a perfect casting every time. Robot arms are used to extract the metal component from the die. This highly automated, computer-controlled system needs constant monitoring both of the castings and the die itself. To check that the casting has been completely ejected from the mold, the robot holds it in front of infrared sensors to check that it's complete. For aluminium alloy castings, like these bodies for car pumps, the machine can be programmed to deliver up to 70 castings an hour. The speed of the process depends on a very fast cooling rate, and careful die design is essential. The high output justifies the high cost of the dies, which are made of special die steel. It's an ideal process for all non-ferrous alloys, and even for high melting ones such as brass or even steel, where obviously the higher the melting point of the alloy, the lower the life of the die. Although the process does demand expensive dies and complex machinery, it's ideal for mass-produced pressure castings. It can be relied on to produce good dimensional accuracy and a good surface on even the most intricate form. Walls can be very thin, and the size of the components that could be made using this high-pressure die casting technique is increasing all the time. If small numbers of specialized castings with high tolerances are required, made of high melting metals, then investment casting is frequently used. It's an ideal method for light alloy materials which need good dimensional accuracy and little final finishing. It's just the thing for making bioengineering components like these artificial hip joints. It's also widely used in the aerospace industry for all sorts of components. This support strut is a typical product of investment casting. A lot of pre-production planning is needed before any components can be produced. Discussions will involve all sorts of people. The salesman who actually won the order, the design engineer who will be responsible for building the die, the metallurgist who will be concerned with the metals involved, and the production engineer whose job it is to make the actual component. Getting everything right at this stage should guarantee that the component will be made on time and at the right price. In this case, because a high-melting stainless steel was going to be used, the only choice was investment casting, using The lost wax method. The key to the whole operation is the die, from which not the components, but the pattern for the components will be made. As the die will be used over and over again, it's got to be exactly right, and obviously it's looked after very carefully. The die is prepared for wax injection by spraying it lightly with oil. This will help prevent the wax pattern from sticking to the die. A soluble core is then placed in the die, and the whole thing is bolted down. Then the wax is injected. 30 seconds later, it's ready for opening. The wax pattern of the aircraft strut with its center core is removed. Because it's so delicate and brittle, it's examined for defects with great care. Then it's placed in a very dilute solution of hydrochloric acid. This will dissolve out the soluble core. After 12 hours, the central core has been washed away, leaving the wax pattern ready for the next stage. The real attraction of investment casting is that you can have a whole range of different components all undergoing the same basic procedure at the same time. These wax patterns are for surgical implants. As they're so small, they're built up on a frame known as a tree. This is very economic because it means you can get a lot of small castings from one melt of the furnace. They need careful handling at this stage as they're very brittle and any breakages are costly. The tree carrying the support strut pattern is cleaned. First it goes into a mixture of isopropanol and trichloroethylene. Then into pure isopropanol. Then it's dried by compressed air. The next stage is to give the wax pattern a ceramic coating, which will eventually form the final mold. This is done by dipping in zircon. It has to be checked to see that it's completely coated. Then it's coated again with a fine refractory powder. Now the entire surface of the wax pattern is covered with a ceramic coating. It's now known as a mold. But even this is not enough to withstand the high temperatures of casting. So after drying for 24 hours, the mold is placed on this automatic machine and the coating process is repeated. The molds are dried by passing them through an ammonia vapor. Then they'll be ready for de-waxing. First they're placed in a steam autoclave, and from there they go into a 900 degree centigrade gas-fired oven. It's absolutely essential to lose all the wax, hence the name, the lost wax process. Any wax left could ruin a very expensive casting. All the trees can then be cooled and left to stand on shelves. They're extremely heavy now, but still brittle. The molds are heated again for 4 hours in a furnace, and they're then ready for casting. A high-quality stainless steel is being used to make the metal strut we saw earlier. It's vital that all the metal in the furnace should be at the same temperature, in this case 1650 degrees centigrade. When the induction furnace has reached that temperature, a small amount of silicon is added to help the metal run more easily in the mold. The temperature is given a final check. The mold is placed upside down on top of the furnace, and then the whole lot is tipped over. When all the molten metal has run into the ceramic mold, it's removed to allow it to cool. A powder is added to ensure that cooling is uniform throughout the mold. About 20 minutes later, the mold is taken to racks, where the metal is allowed over a period of about 24 hours to cool to room temperature. Knocking the ceramic covering from the metal casting is a dusty, noisy business, but it's still the most efficient and safest way to do it for this particular casting. The surplus metal runners and risers are removed, and after final finishing, the strut, like all the other components made here, is given a series of rigorous tests. X-ray analysis is used to detect deep cracks. This strut has such a crack, which shows up as a dark mark on the photograph. This one, though, is perfect. No dark patches. Surface defects are revealed by examination under ultraviolet light. If the component is passed at this stage, it's then tested for dimensional accuracy. The thickness of the metal along any one of these faces must be within the limit specified by the customer, and so too must other vital dimensional criteria. Investment casting is an ideal process for forming metals that can't be successfully machined, tungsten, for example, and cobalt. And with its varied possibilities for making small or large components, it's a profitable method of production. But whatever technique of casting is chosen by the engineering design team, as we'll see, there are an increasingly exciting number of alternatives available when it comes to shaping and forming materials.